All right, ladies and gentlemen, today's class recording has started. So yesterday, as I move the microphone and probably make a lot of noise while doing it. Yesterday, we introduced the concept of electric charge. Where do electric charges come from?
Subatomic particles.
Good. Electric charges come from subatomic particles. John, namely which two subatomic particles?
Electrons and protons.
Good, right? We talk about subatomic particles, they come from electrons and protons, right? And we talked about the idea that depending on how many electrons and how many protons an atom contains, it can then either be charged positively, negatively, or not charged at all. If the number of protons and electrons is the same, it's not charged. If it has more electrons than protons, it's negatively charged. If it has more protons than electrons, it has a positive charge. How does something gain a negative charge? By gaining electrons, all right? Something gains a negative charge by gaining electrons. How does something gain a positive charge? It loses electrons. It does not gain protons, right? So we always talk about charging items by what happens to the electrons. Does it gain electrons? If it does, it's a negative charge. If it loses electrons, then it has a positive charge, okay? We talked about we talked about two ways that can happen. So the first way that can happen we call charging by friction. What has to occur in order for charging by friction to happen? Contact, but what also has to happen? Movement, right? We got to have that movement to create the frictional force to move those electrons. We said that certain types of atoms are better at picking up electrons. Certain types of atoms are better at losing electrons. It depends on what kind of an atom is it metal or non-metal? How many valence electrons does it have, etc., etc. We'll talk in more detail about that in the next unit when we get into chemical bonding. All right? So charging by contact requires movement. Charging by conduction requires what? Straight contact, right? Where electrons are transferred through contact. Again, depending on what type of atoms we're talking about, that's going to determine which way the electrons flow. One specific type of charging by contact we talked about yesterday was grounding. When we ground something, what are we doing? We're connecting it to what? The earth, right? And that allows electrons to either move into the earth or move out of the earth. But because the earth is so big, it doesn't necessarily end up with a positive or negative charge, even though it gains electrons or loses electrons. Okay? Good there. All right. A third type of charging we call charging by induction. And to demonstrate that, I'm going to take us back to the camera. And let's take a look at the electroscope again. Okay? So in case you don't remember the electroscope, let me get this stuff out of the way so you can see a little better. In case you don't remember the electroscope, right? Rabbit fur, I'm rubbing it on the table behind the electroscope. Charging by friction, right? And so then I'm going to take this the aluminum circle, right? And put it down on the table where I was charging by friction, touch it real quick, and then if I bring the aluminum sphere close, I can get those aluminum foil leaves that are laying there to sort of move apart temporarily. Yes? And then if I take the aluminum foil thing, or if I take the metal sphere away, they fall back, right? And I accidentally touched the electroscope, so I have to charge this thing up again. So, yeah. Good. Hold on just for a second, and I'll explain that to you. Okay? So, yeah, we have to talk about induction before that happens. So, okay. All right. So, if I bring it close, right, they move apart temporarily, and then they go back to falling straight. Temporarily move, fall back to straight. But then if I touch it, charging by conduction, and they stay apart, right? So let's talk about that temporary movement of the aluminum foil leaves away from each other, and then they fall back once I move the metal circle away from it. All right. I believe you have this picture on your outline, so if you want to follow along or make some notes, you most certainly can do so. Okay. Oh. First of all, induction only happens in conductors, and here's why. So, here we have two metal spheres labeled A and B. Right now, they're two separate spheres, but they're touching. So if they're touching, they're basically one object, okay? If we look at the combined spheres A and B and count up the number of positive charges and the number of negative charges, what do we see? Somebody said it. What do we see about the number of positives and the number of negatives combined? They're the same. So, does this combined object actually have a charge? No. But here we bring this object that previously had been charged, probably through friction by rubbing it on a cloth or something like that, right? It has a bunch of extra negative charges. Even though within the two metal spheres A and B we have the same number of charges, remember that in metals and conductors, those electrons can sort of move easily between one atom and the next atom. Does that sound familiar from our discussion yesterday, right? So when this hand brings in a negatively charged object close to these two metal spheres, where do all the negative charges, not all the negative charges, but where do the negative charges in the metal sphere tend to move? If the hand is bringing something negative, what do the negatives in the spheres try? They try to move away because of the whole repulsion thing, right? So even though A and B together have the same number of positives and negatives, we have positives left sort of on A by themselves and negatives that have sort of migrated over to B. This makes A and B almost behave like a magnet. It's the same object, but the two sides are acting differently. Is that, or can we see that that's almost kind of like a magnet, right? The same thing happens with the electroscope. I don't think this is charged anymore, but okay, grounding. When probably isn't charging anymore. Yep. Let's use the first side. That works better. So it's a good thing this is on recording, so you can go back and watch this. So, all right. When I bring this negatively charged sphere close, the electrons that are up here in the metal knob don't like the negative electrons that are in this sphere. So where do they go? They go away. They head downwards through the metal post and towards the aluminum foil spheres. But now we have a bunch of extra electrons down in those aluminum foil sphere, or the aluminum foil leaves, right? So what do they do to each other? If you have a bunch of extra electrons around there, what do? They push each other apart. But it's a temporary thing, because those extra electrons are only down there because they don't want to be close to this. If I take this away, what do those extra electrons that got pushed down there do? Head back up to the top so they can spread themselves out even more. So we get this temporary movement of those charges, or temporary movement of the leaves. Weird because they're moving towards each other, but that's okay. All right. But then, once I actually touch, and the extra electrons are transferred into those aluminum foil leaves, they permanently stay apart, right? or until I ground this and all the electrons spread themselves out back into the Earth. Okay? So, Fiona, with your original question, why do I have to touch this? The same thing of the movement of the electrons is actually happening with the table and this aluminum foil sphere as well. Okay? So by touching it, that's similar to this situation. Here, A and B together technically have the same number of positive and negative charges. So these objects together are technically not charged. They just have charges separated within the same object. But if when they're separated like this, I pull them apart, now B does have more negatives than positives, and A does have more positives than negatives. That me touching this the metal sphere here is basically the equivalent of pulling these two spheres apart, and I give this thing an actual charge. Excuse me. That'll sound good on recording. So by touching it, I actually give this thing the actual negative charge, and that's what causes that to happen. Okay? All right. Induction only happens in conductors, and it's sort of a temporary movement of charge within those objects. Okay? All right. We know that objects that have the same charge repel each other, objects that have opposite charges attract each other. That can cause them to move. We've seen that with the pith ball. We've seen that with the little foils on the aluminum foil leaves that are hanging there. You saw it with the stream of water in the demonstrations that we did on Monday. Movement requires force. That's how things move, through forces, right? We talked about that earlier in the year with acceleration and all that fun stuff, okay? So, if electric charges can cause other things with electric charge to move, they have to apply a force. And we call that force, or we summarize that force, with something called Coulomb's law. I introduced the term Coulomb to you earlier. It's how we measure the amount of charge something has. But Coulomb was a guy, and this law was named after him. And it's the amount of force that two charged objects can apply to each other. So, I think you guys have this written down in your outline, right? Let's talk about what the different parts are. First, Q1 and Q2. That is the amount of charge that the two objects we're talking about have. Okay? Positive charges can only exert a force on other charges. It might be positive, it might be negative. But if I charge up this plastic rod by rubbing it along the silk tie, right, charging by friction, this plastic rod ends up with a charge. But if I bring it close to the roll of tape, does anything happen? No, because that's not charged, right? We have to have two objects that have an imbalance of protons and electrons for this to work. Q1 and Q2 are how big of an imbalance do we have between protons and electrons. And then D is the distance between those two objects. I can charge up the plastic rod by friction, rubbing it along the silk tie. But if I hold it over here, can I make the pith ball move? I have to bring it close to make that pith ball move, right? The amount of distance affects how much force is there, right? So let's talk about fractions. The amount of charge is in the numerator of this fraction. If the numerator of a fraction gets bigger, what happens to the answer of that fraction? If the top of a fraction gets bigger, what happens to a fraction? Is a division problem, right? If the top of a fraction gets bigger, what happens to the answer? It gets bigger. What do we call that? It's a direct relationship. So force is, Roman numeral 4, letter A. Force is directly related to the amount of charge. The greater charge an object has, the greater force it can exert on other objects. But those other objects have to be charged as well. D, the distance between the two objects. Where does that show up in our fraction? Denominator. If the distance increases, what happens to the amount of force? It gets smaller. What do we call that? That's inverse, right? An inverse relationship. But if we look here, right, what are we also doing to D in this equation? We're squaring it. So we refer to this as specifically a specific type of inverse relationship as an inverse square relationship. That is something that shows up an awful lot in nature. Okay. So an inverse relationship would mean if we took two charges, if they were 1 inch apart and we made them 2 inches apart, an inverse relationship would say there's half as much force. But an inverse square relationship says if we go from 1 inch apart to 2 inches apart, now there's not half as much force, there's 1/4 as much force. Because there's a 2 on the bottom of that fraction, but we're squaring it. Does that sort of kind of make sense? Do we follow that? Okay. Inverse square relationship. So, these charges can exert forces on one another. But electric force is similar to gravity in the following way. I can charge up this plastic rod by rubbing it along the silk, charging by friction. I bring it close to the pith ball and the pith ball moves away from it. Repulsion, same charges. But what doesn't have to happen in order for the pith ball to move away? Bad question. Sorry. Do I actually have to touch the pith ball to make it move away? No. If I want to move that roll of tape, though, what do I actually have to do? I actually have to touch it, right? So here we have an example, much like gravity, of something that we call a field force. Certain forces, specifically gravity, electric charge, and magnetism, have the ability to affect other objects in the space around them, even though they do not actually touch. All right? That was a problem for a long time. How can there be how can there be force if there is no contact? So, in the 1700s, an English scientist named Michael Faraday comes up with an explanation. Have you guys learned about Faraday in history? Really? Lost. I don't watch Lost. So. I mean, it's not on anymore, but so Michael Faraday comes up with something to explain what we called at the time action at a distance, or the ability to do stuff even though we're not actually touching. And he comes up with this idea or a theory that he calls a force field. A force field is an area that surrounds an object. In that area, it can affect other objects. Right? You're familiar with this force field most of all. Okay? You don't have this picture, but when I was looking back at this presentation from last year, I was pretty proud of myself for drawing that picture of the Earth and filling it in the way that I filled it in so well. And so I was like, I need to keep this picture. So, right? So, this picture represents the gravitational field that surrounds the Earth. What does Earth's gravity do to stuff? pulls it in, right? What do all the arrows that surround the Earth point? Or how do they all point? They all point inward, because that's what gravity does to things. We refer to those lines as the field lines that explain what gravity does to things, right? Same idea, different situation. So here's a baguette that apparently has a bag of bread that has obtained a negative charge somehow. I don't know, but let's say that it has. Okay. So here we have this object that has obtained a negative charge. We know that it can attract oppositely charged things or repel like charged things. Again, in the area that surrounds it. So if this is the gravitational field, because it's what gravity would do to things, what do you think we're going to call the space that surrounds something that has an electric charge? If this is the gravity field, this will be the electric field, right? So the electric field is the area that surrounds a charge. Let's take a look at these two pictures. You have these pictures at the bottom of the back side of your outline. They might not have copied real well, so if you want to like highlight the arrows a little bit, you can do so. But knowing which way the arrows point are important. So here's the electric field that surrounds a proton. Here's the electric field that surrounds an electron. Both of them have arrows, but what are you noticing about the arrows? They're opposite, right? So, because electric charges come in two varieties, we have to distinguish. So when we talk about the electric field, we always talk about what would happen to a second positive charge. So, if we brought another proton close to, oh, I need an actual pen here, right? If we brought another proton close to this proton, what would happen to it? It'd be repelled, and that's why that arrow points outward. Regardless of where we took this proton, if we brought it up here, it would still be repelled. If we brought it over here, it would still be repelled. So those arrows, which we call the field lines, represent what would happen to another proton. Jack, go ahead. So, we always draw the field lines in relation to what would happen to a proton. We just have to know, okay, an electron would do the opposite thing, right? So here, proton would be pushed away. Here, right, if we put a proton in that space, it would be attracted, right? So Jack, we just have to know that an electron would do the opposite of that. We had to pick one or the other, so we picked positive charges and said, okay, just knowing that negative charges are opposite, they would just do the opposite thing, right? So these are the fields that surround like a single proton and a single electron. But we can also talk about what would happen if we put multiple charges close to each other. Notice here, there's a bunch of arrows, but they all follow sort of a similar pattern. All the arrows are pushing away from the proton and pushing towards the electron, right? Does that make sense when we see all of them up there, right? They all point away from the proton and they all point towards the electron. Because if we put a second proton, it won't stay there, right? It wants to push away from this proton, but it wants to push towards this electron. That's why the arrows point that way. The field lines, those arrows show us what would happen if we put a proton in that spot. Okay? And then finally, here's two protons. Notice, none of the arrows point towards either of them. Because regardless of where we put a third proton, it wouldn't go towards any of them. Hold on, fast question before we put stuff away. What would happen to that proton? It would push the other two away, but would it go anywhere? It would not go anywhere. The proton on the left would push it towards the right. The proton on the right would push it towards the left. Notice, are there any arrows in that spot? No. The electric field in that spot is 0 because the electric field from each individual proton cancels out the other one. So nothing would happen there, right? Or if we want to use a term from a long time ago, that proton, that third proton that we put in there, would be in equilibrium. Think about that, right? That's, right? It's a long time ago, I know. All right, tomorrow we'll start talking about some batteries.